Now we're going to talk about a very important and general principle that when you have a system of linear equations, the solution to that system can be thought of as broken up into two parts. There's a particular part and there's a homogeneous part. The particular part is only a constant, and the homogeneous part is the part with parameters. Okay? Now, if you go back here, you can see that what we have here, it follows this form. Here's the particular part here, and then this here is the homogeneous part, because this part has parameters. Okay, so this satisfies the form. I say that this is a very wonderful result because it doesn't just hold for algebraic equations, it holds for other types of linear equations, and when you take differential equations, you'll see this very same expression that works exactly the same way. Okay, so let's give an example. Okay, so here we have this system. Okay, this is the same system we had before. Our solution xyzw can be expressed as a constant vector plus z times one vector plus w times another vector. Okay, now if we take z equals w equals 0, then that means that this term will go away, this term will go away, and in fact this vector is a particular solution of the system. This is one possible solution for x, y, z, w. Okay? All right. Now, a linear equation is homogeneous if it has a constant of 0. So it can be written in this way. We have our linear combination on the left, but you have 0 for the constant term. Okay? Now, here we had a system of equations here. This was not a homogeneous system, but we can write the corresponding homogeneous system that has zeros in the constant positions here. So take a look at this system. This is the very same system, but I've replaced the constants with 0. I can apply Gauss's method to this system. If I do so, I get a system like this, and you can work out that the solution to this system is in fact this combination of vectors which is parameterized by z and w. Okay? Notice that this solution here is exactly the piece of the solution here which I set to 0 when z equals 0 and w equals 0. So in fact I can divide my general solution into two pieces, one where I set z equals 0 and w equals 0, that's a particular solution, another where I allow z and w to vary, which gives me the parameterization of my entire solution. Okay. All right. Now, here we want to prove our results for any. So we take a lemma. Lemma is kind of a helping theorem that enables us to prove a more important result. All right. So now, for any homogeneous linear system, there exist vectors b1 through bk such that the solution set of the system is c1b1 plus ... plus ckbk. What is this saying? This is saying that for a homogeneous linear system, the solution is a linear combination of vectors, and in fact, it's arbitrary linear combinations. These c's are arbitrary. I can set in any values at all. The number of vectors in this solution will be equal to the number of free variables in the echelon form version of the system. All right, let's look at an example. Consider this system of homogeneous equations. Okay. Now, if we eliminate the, well, this is already in echelon form. Okay. I have two free variables, w and z. I can write this leading variable as a combination of the two free variables. Once I've done that, I get this result. I can go to the first equation and replace this leading variable by its expression in terms of free variables. Okay. And that will give me this result. So my two equations in the echelon, when I do my reduction, I get x equals minus 2z. And I also get y equals z minus w. And I could write this as plus 0 times w if I want to. Okay. So notice that this breaks up very naturally into vector equation. xy is equal to, these two multiply by z, so I take z here, and here I have minus 2 and 1. And here I have plus w, and here I have 0 and minus 1. Okay, so in this case we see that we have a vector solution, which is a linear combination. This z plays the role of c1, this w plays the role of c2. We have two vectors here that corresponds to the two free variables here. So this example does indeed fall into the description of this lemma. Okay. All right. Now I didn't actually finish the solution. And I should thank the author for completing the solution. I only wrote the first two components of these vectors. For a complete solution, you should also write the variables z and w, because those are variables in the system. And this just expresses z equals 1, and z equals z, and w equals w. And so here we have the two vectors beta 1, beta 2, and the two constants c1 and c2. Okay, for the proof of this theorem, this lemma rather, I'm going to go back to the textbook, which gives a little bit more detail. Now, I think that many people will find the details of this proof difficult. I'll try to go step by step. If you don't understand completely the first time, don't worry about it. This is kind of a first introduction to rigorous mathematics. Right, so let's go back over the statement of this lemma. For any homogeneous linear system, there exist vectors b1 through bk, these are column vectors, such that the solution set of the system is a linear combination of these column vectors, where the constants are arbitrary real numbers. Here k is the number of free variables in an echelon form version of the system. Okay, so the number of vectors that occur in the expression of the solution of the homogeneous equation is equal to the number of free variables. All right, so let's go down here to the start of the proof. Okay, and the point he makes here is that this previous example is an example, not a proof, but the example gives us an idea of how to do the proof. In the example, we move row by row up the system from the last row to the next to last, and so on. This points to doing the proof by mathematical induction. Why does it point to mathematical induction? Well, you're doing it step by step, and each new step depends on the accomplishment of the previous step. Okay. I think some people, when they hear the word mathematical induction, their blood runs cold. There is an appendix in the book that discusses induction, and I invite you to go there. It's on page, I thought it was 472. Let's see if we can find it. It's down here somewhere. Okay, it's in the appendix. Okay, here we go. It's on page, well, they call it A4. All right, so in induction, there is always a base step and an inductive step. And I won't say more about this appendix. He does a couple of examples that you can read. And I think once you read several induction proofs, you begin to see how things are going. So let me go back to the case at hand, and we'll follow through that. That's page 26. Okay. All right. So in this case, we're going to do induction in two steps, as always in induction, a base step and an inductive step. Okay. In the base step, we verify that the statement is true for some first instance. Here, that for the bottom equation, we can write the leading variable in terms of free variables. In the inductive step, we must establish an implication that if the statement is true for all prior cases, then it follows for the present case also. Here we will establish that if for the bottommost t rows, we can express the leading variable in terms of free variables, then for the t plus 1 row from the bottom, we can also express the leading variables in terms of those that are free. And once we can express the leading variables in terms of free variables, we can write a vector equation for the solution, such as we've seen before in the particular examples that we've done. Okay, let's follow. Whoops. Sorry, lost it. We'll get there. Okay. All right, these two steps together prove the statement for all the rows, because by the base step it is true for the bottom equation, and by the inductive step, the fact that it's true for the bottom equation shows that it's true for the next one up. Then another application of the inductive step implies it's true for the third equation up, and so on. Now, notice that this is exactly what we did in the specific examples that we worked. Right, just following that same format, but trying to formalize it in a general way. All right, so let's start the proof. First, let's apply Gauss's method to get to echelon form. There may be some 0 equals 0 equations. We can ignore these because 0 equals 0 is always true, and there are no leading variables. Right? So we don't need to worry about leading variables. Because the system is homogeneous, there are no contradictory equations. We can always set all variables equal to 0 and get a solution to the system. We will use induction to verify that each leading variable can be expressed in terms of free variables. That will finish the proof because we can use the free variables as parameters, and the betas are the vectors of coefficients of those free variables. Okay, again, refer yourself to the specific examples that we did, where we were able to get the solution as a linear combination of vectors. All right, so I have written here system of equations in echelon form. I haven't written the equations, but this is the augmented matrix that represents the equations in echelon form. And you can see the stair-step shape of the echelon form matrix. Okay, so it may be a little bit confusing, this notation here. All right, I started the matrix here with A11 through A1n. All right. It's always possible to arrange your variables such that the first variable has a non-zero coefficient. Right. But when I go down to the second row, notice I have some zeros here. I don't know how many of these variables here, for instance, if I call the variables x1, x2, x3, etc., I don't know how many of the variables x2, x3, x4, etc. are going to be free variables. All I know is that after some number of zeros, there should be a non-zero entry, and there will be a first non-zero entry. As we talked about before, if all the entries are 0, we don't need to worry about that equation. All right? So to indicate that the first non-zero entry is in some position, but I don't know exactly which position, I put the indices like this. I know that I'm looking in the second row, so that's why I have a 2 here. But the column index I call L2. And the L stands for least. And this entry here is going to be the first non-zero entry in this row. Okay? And that means that the variable corresponding to this column is going to be a leading variable. All right? Now, if I go to the third row, I can do something similar. I know I'm going to have some number of zeros in front, at least 2. I don't know how many, could be more. And then the first non-zero entry in that row, I'm going to call A3, L3. Again, I'm not sure exactly what L3 is, what the value is. It's at least 3, but it could be more. But L3 is defined so that this entry is non-zero. Okay, and then I have some number of other entries. These could be 0 or non-zero. It doesn't matter to me. And then I come to the last entry here. So I continue this pattern to express all of the rows of my matrix in echelon form. And this is the form that is going to be used in the proof. So let me jump back to the proof here. Okay. So here we have the bottommost equation. So go back here. So the first coefficient is AMLM, and that's going to multiply the variable x sub m. Right? The variables correspond to different columns. This column corresponds to variable x sub 1. This column corresponds to variable x sub 2, all the way up to x sub m. This is the LM column, so this is going to correspond to the variable x sub LM. Okay? So if I write this equation out, I start with XLM, then I'm going to have XLM plus 1. Okay, this plus 1 is part of the subscript, all the way up to xn. So you can verify that this equation expresses the last row in the row echelon form. Also, what's important is that this value here is not 0. Since this value is not 0, that means I can solve this equation for XLM by moving everything to the right and dividing by the leading coefficient. And that gives me XLM. Now, this is exactly what I wanted. I found the leading variable in this last equation in terms of the free variables. Okay. You can read this technical point. I think it's really, you have to be a little bit careful when everything is 0, but that's not a big issue. All right. Now, so we've finished with the base step. We've shown that with the last equation, we can write the leading variable in terms of free variables. Now, so let's go with the inductive step. Now, I think there's a little mistake here in the textbook. Instead of this being 0 less than or equal to t less than or equal to m minus 1, this should be a 1 here. Okay, and this should be an equal then. Okay, so we've already shown it for the bottommost one row, and let's assume that we've shown it for a certain number of bottommost rows, where the bottommost row could be 1, could be 2, all the way up to m minus 1. Okay, so more explicitly, assume for the m equation and the m minus 1th equation, up to and including this, instead of this, this should be m minus t minus 1. Okay, because the bottom equation is the m minus 0 equation, second from bottom equation is the m minus 1 equation, and so on. Right. So we're assuming that we have proven this statement for the bottommost t rows. Okay, and that means the row with index between m minus parenthesis t minus 1 all the way up to m. Right? Now m minus t minus 1 is actually m minus t plus 1. Right? So we've shown up to the m minus t plus 1 row and beyond that the leading variables can be expressed as linear combinations of the free variables. We want to show this now for the m minus tth equation. Okay, so this should be m minus t here. Okay. Okay. Now for that, take each variable that leads in a lower equation. Okay, xlm xl up to xlm minus t. In other words, let me go back to my picture here. All right, we're considering now the m minus tth row. So let me write that here. It's going to be somewhere in here. We'll have zeros up to here. Then we'll have a, and this is going to be m minus t. And then this is L sub m minus t. And then I'm going to go to a, m minus t, and n. Okay. Now notice that in this list of coefficients, there are going to be coefficients for several leading variables. For instance, XLM is going to be a leading variable that appears in this equation. However, since we've solved for XLM, we can plug in the expression for XLM into this equation. If you remember, that's exactly what we did in the specific examples. Okay, all right. So let's see. All right. So for that, we take each variable that leads in a lower equation and substitute its expression in terms of free variables. We only need expressions for leading variables from lower equations because the system is in echelon form, so leading variables in higher equations do not appear in this equation. What does that mean? Well, for example, here's a leading variable, x1, in a higher equation. This leading variable does not appear in this row because all of these coefficients are 0. Same in this case for x2. Well, actually, this would be xl2. xl2 is a leading variable for a higher equation. It does not appear in the m minus t row. Does not appear in the m minus t row because there's a 0 here. All right? The only leading variables that appear in this equation correspond to lower rows in the system. Okay, right. So what we have then is an equation which has only the leading variable. This should be x m minus t. This should be m minus t, m minus t, m minus t, m minus t. Okay, and everything else is a free variable. Move all the free variables to the right. Divide by this non-zero coefficient, and that gives us the leading variable for that row. And again, this is just replace all the t plus 1s with t's. And we've expressed this in terms of free variables. So we've done the base step and the inductive step. So by the principle of mathematical induction, the proposition is true, and we finished the proof. So you can breathe a sigh of relief, and I suggest you go back over this proof again, read it yourself, watch the video again, and eventually you'll get the idea. You shouldn't expect in mathematics to get things the first time. It usually takes several times to get it. Okay? Okay. Now this shows, as discussed between the lemma and its proof, that we can parameterize the solution sets using the free variables. We say the set of vectors is generated by or spanned by the set of vectors beta 1 through beta k. Right. Now, to finish the proof of theorem 3.1, the next lemma considers the particular solution part of the solution set's description. Okay, so let's review what we've just proved. We've just proved that any homogeneous linear system has a solution that can be written as a linear combination of vectors. Now we want to complete the proof that any linear system, homogeneous or otherwise, can be written as a sum of particular plus homogeneous solution. And that's this lemma here. For any linear system and for any particular solution P, the solution set is equal to that particular solution plus a vector H, where H satisfies the associated homogeneous solution. So homogeneous system. Okay. And we saw this again in several particular examples. Now we want to prove it in general. Okay. Okay. So we're going to prove this by showing set inclusion two ways. We're going to show that that this set P plus H, we're going to show that the solution set is, let's see how we're going to do this. Let's make sure that we're going to do this. We're going to show that any solution can be written in this way. Okay? That means that the solution set is a subset of the set of all vectors satisfying this condition. Okay? So we're going to show that every solution satisfies this condition. Okay? All right, so and then in order to finish the proof, we'll have to show that every vector that satisfies this condition is also a solution. Okay? All right, so let's say, okay, so suppose that the vector solves the system. In other words, suppose that we have a vector that is in the solution set. Okay? And we'll call that S. Okay, so S is in the solution set. Okay. Okay. Now, let's see what happens with S minus P. All right, so let's write down the equation satisfied by S minus P. All right, we multiply S1 minus P1 times the first coefficient plus plus Sn minus Pn times the nth coefficient. I can rewrite this by expanding and collecting the terms with S and the terms with P. All right. And according to the fact that S is a solution, I know that this sum here is going to be di, which is the constant term. And this sum here is going to also be di because P is a particular solution. All right, so I'm going to get 0. And that's true for any equation I. All right, this was a way of writing the ith equation. And for any of the n equations, I can write in this way. I can show that the S minus P is going to satisfy the homogeneous version of that equation. Okay, so that means that S minus P is a homogeneous solution, so I can write S minus P as H, and that means, in other words, that S is equal to P plus H, which is exactly what I wanted to show. Okay. Now let's take set inclusion the other way. In other words, any vector of this form will also be in the solution set. All right, and we do a similar proof. We have a system of n equations. Let's take the ith equation and plug this vector in and show that this vector satisfies that ith equation. All right, so if we do that, the ith equation has coefficients specified as follows. If I plug P plus H into this equation, I'm going to get these components of the vector. And again, I can do my expansion and collect the P terms here and the H terms here. Now I know that P is a particular solution, so that's going to give me di on the right-hand side. And H is a homogeneous solution, so that's going to give me 0 on the right-hand side. So that means that this P plus H vector is going to satisfy the original system of equations because I end up with a constant di. All right? So in other words, P plus H is a solution to the system of equations. And I'm done with my lemma. Okay, let's do another theorem. Any linear system solution set has this form: P plus the sum of linear combination of vectors, where P is a particular solution, and the number of vectors is equal to the number of free variables. All right, so what we've just done here is we've combined the two lemmas, and we've shown that the homogeneous solution has this form, and we've also shown that the set of solutions to a linear system is particular plus homogeneous. So here we've just summarized the contents of the two previous lemmas. Okay. Now, a corollary to this theorem is that solution sets of linear systems are either empty, or have one element, or have infinitely many elements. Okay. All right, we've seen examples of all three happening, so we only need to show that there are no other possibilities. Okay. So let's look back here. I'll talk through this, but let's look back here. We know that the solution has this form. All right. Now, if any of these betas are non-zero, and there is in fact a particular solution, then we can see there is an infinite number of solutions. Okay. If all of the betas are 0, then there is only one particular solution P. And it's also possible that the system has no solutions. Okay, so that really covers the three cases. If we have a non-zero beta, we have infinite number of solutions. If we have all betas 0, we have one solution. And if there's not even a particular solution, then we have no solutions. So let's talk through these words here. Okay. All right, so here first, observe a homogeneous solution with at least one non-zero solution. V has infinitely many solutions. This is because any scalar multiple of V also solves the homogeneous solution. And there are infinitely many vectors in the set of scalar multiples of V. Okay? That is, if S and T are in R and they're not equal, then ST is not equal to TV, since the difference of the two vectors will be a non-zero multiple of V. Okay? And if I take a non-zero multiple of V and consider the non-zero components when multiplied by a non-zero number will also be non-zero. Okay? So this establishes that if I have a homogeneous solution that has at least one non-zero solution, then it has an infinite number of solutions. Okay. Now we can apply lemma 3.7 to conclude that a solution set is either empty, that is, if there's no particular solution P, okay, or has one element if there's a P and the homogeneous system has a unique solution 0, or is infinite if there's a P and the homogeneous solution has a non-zero solution. Okay? Now, I'll probably take you a few times to read through this. It seems very convoluted, but I'm hoping that you'll get used to this way of expressing things. What you're just doing in proof is generalizing the same things that you do in particular cases. And usually that's what mathematicians do. They go from particular case and try to write it up in general. Okay? We can summarize the possibilities in this table. Okay? So if there is a particular solution, we're in the first row here. If there's only one solution to the homogeneous solution, that is the 0 solution, then the system of equations has a unique solution. On the other hand, if the homogeneous solution has a non-zero solution, that means there are infinitely many solutions to the homogeneous system, and that means there's also infinitely many solutions to the system of to the original system. Now, if there's no particular solution, then there's no solutions for either case. Okay, an important special case is where there are the same number of equations as unknowns. Let's give a definition. The square matrix is non-singular if it is a matrix of coefficients of a homogeneous solution system with a unique solution. It's singular otherwise, that is, if it's the matrix of coefficients of a homogeneous system with infinitely many solutions. Okay. All right, we're done, and that's it.